Okay, I hope the screen and all is visible. I'll just see a quick recap of where we were like last time and continue from there. Okay, right. So I'll quickly summarize in a bit of where we were, uh, and you can ask me questions if you have anything from our last discussions. Okay, so uh, the idea was to have a general framework for optimization. And so we started off with minimizing a cost function of the form f of x. And then we also looked at, well, so in many cases, we may have constraints, right, such that h of x equal to 0. And this we broadly termed as equality constraints. Okay, so in within this, we looked upon of how to. So for the just for the unconstrained case, I was just looking at the gradient uh, condition, and we had this first order necessary, and also in cases some first order sufficient conditions for first and second order, or the second order sufficient condition and the first order necessary condition for optimality in an unconstrained case. Things get a little exciting when I have a constraint on the system. In some cases, it also helps us to, for example, if I just look at a function minimize x1 plus x2, for this solution doesn't exist, right? So if I just draw contours of my function of x1 plus x2, they look something like this, and for which a minimum does not exist. However, things get exciting when I say, look, we minimize this function subject to uh, x1 square plus x2 square equal to 2, which means I'm kind of around this circle of radius 2. Okay, and then okay, now I can see that, well, the minimum of this function actually exists like somewhere here. So it's not always that having constraints in my problem makes my problem a little difficult, and so on. Okay, so what did we derive last time was we had the first order and second order conditions for this. So uh, we uh, we went about our search set to have conditions of the sum. I'll just maybe summarize those conditions here that I define. So in this case, my first order necessary conditions are of the form gradient of f of x is the gradient of h of x, and h of x was equal to 0. Or I can just look at the Lagrangian as f of x uh, plus lambda h of x, where this would just be that I'm now computing the gradient of L to be 0. So this turns out to be the gradient of L with respect to h, and the second condition turns out to be the gradient of L with respect to lambda. Okay, so this is where we were, and we also looked upon uh, so looked upon things like what happens at the optimal point. What happens at the optimal point was that the if I have a picture to project that uh, the contours of fx were collinear with the tangent of h of x. So um, uh, these were the points, and we could therefore so the geometry of this was that at the point of minimum, the contours of fx are collinear with the tangent of the h of x. So that you could see somewhere here. Or in other words, the gradient of f and the gradient of h are also collinear with each other, and that's the geometry of this, and the calculus of that is pretty neat. So this is where we were last time. Okay, so just to recap, at the optima, the gradient of the cost function is orthogonal to the set of feasible solutions. Okay. Now, what does this also mean in terms of the larger geometry? So, if I look at now, so how did we look at the first order, second order necessary conditions and sufficient conditions for unconstrained case? Was we looked at around like the Taylor series expansion and so on. So suppose now in this case, I am looking at maybe in a bit of a higher dimension case, I'm looking at a surface. Okay, when I'm in a curve, things are easy, right? So if I'm kind of looking at a minimum of this function, I'm just moving just along this this function of one variable. Whereas if I am on a surface, so if I'm on a 3D surface of this form, then I see, okay, what happens when I start from any arbitrary point and move in any direction, which means I am looking at a curve and see what happens to my function along that curve. So this is a little more generalization. So let me call x a curve x that is parameters by alpha, and I see what happens as I move. What happens to f along that alpha? So f x alpha d over d alpha, I use the chain rule, will give me the gradient of f x alpha, the transpose, and x dash of alpha. What I know that is, okay, so this when alpha equal to 0, I have df by d alpha. X alpha is the gradient of f x 0 x dash 0, and this curve is parameterized such that x at 0 coincides with my optimum point. Okay, and this is 0. Okay, similarly, if I look at h, my set of constraints, h x of alpha is also, so if I look what happens to h along the curve, this will be the gradient of h again times x transpose prime at 0. Okay, so this will also be equal to 0. This is kind of also to show that the gradient of the cost function will be orthogonal to the set of feasible function. So okay, now what about these directions that I generate? Okay, so so not only the gradient of the cost function is perpendicular. So this, if I look at a curve parameterized by alpha, this will now this is the point x star. Then this space will just be like the tangent space to that, right? So what we see is that this equation or this expression means that the gradient of the cost function should be perpendicular to a vector now from the tangent space. Perpendicular to a vector from the tangent space. Okay. Not only that, the same holds for this also, right? So not only that the gradient of the cost function should be perpendicular to a vector from the tangent space, but also the gradient of the constraint function. Okay, so this will also now help me generalize to what if there are more than one constraint. Say there is H1x, there is H2x. I look at how H2x also behaves along the curve parameterized by alpha. So I have a H2, this will be the gradient of H2 transpose times x dash of 0. All this will go to 0. Okay, and this now says that, okay, what if I have one constraint, I can write my first order conditions of this form, and where I know that this gradient of f and the gradients of h are now collinear with each other. Okay, now I have these two generalized conditions now, right? So gradient of f at x star d is 0, and then where do this d come from? For all d for which now I have n number of constraints, right? Hi of x equal to 0. Let's say for I equal to 1 to m. I just don't have one equality constraint, but I have several of them. For all h such that hi x star times d equal to 0. Okay, this is kind of nice to say now that now the gradient of f of x star belongs now to the span. So these are now in the same space because they are orthogonal to D. So this will be this in the space spanned by all these gradients, gradient of h1 till gradient of hm of x. Okay, which means that if this is in the span of this, one of my earlier linear algebra lessons would tell me that if the gradient of f of x star is in the span of gradient of h1 till gradient of hm x star, then any gradient of f of x star can now be written as a linear combination of elements here. So lambda 2, this will be h2x and so on. Okay, so I can now summarize my conditions that gradient of f at x star plus summation over lambda I gradient of hi of x summation over all the m constraints I equal to 1 to m equal to 0. And now I can write a generalized L as f of x plus lambda transpose times h equal to 0. Okay, I can just now have several incorporate several constraints into this. Okay, and this if I summarize from what we had here, will now look something like this. Okay, so where were we here? So this maximization was done. This was nice. This was nice. Yeah. Okay. So I have now an optimization problem. F of x such that this equal to 0. I define a Lagrangian function and then I have my first order necessary conditions. Okay, and as what were the second order? So we'll go to start with constraint optimization to see what was the difference between the necessary and sufficient conditions. Okay, so this was my first order necessary condition for a maxima, and first order sufficient conditions was of this form. And I also had somewhere I had first order sufficient conditions also, right, where the conditions were simply of the form, so if d2f by dx square was strictly less than 0, then this was a sufficient condition. Okay, now what about sufficient conditions for my Lagrangian? So what I actually do here is I start and then I convert my unconstrained problem into a constrained problem into some kind of an unconstrained problem. Okay, now we'll see what happens now to the second order conditions. I'll try and do with the help of an example to see, well, can I derive? So I know the first order necessary conditions now, right? At the uh, first order necessary conditions are simply gradient of f of x is now summation over lambda gradient h of x, and then all the other conditions hi, so lambda I equal to 0. Okay, now what about the sufficiency here? And that is, I think, one of the crucial steps that we will derive here. Any questions so far of where we are going? So we are just to recollect, just looking at constraint optimization with equality constraints. Okay, now let me do a quick problem here and then motivate how do we get the second order conditions. Now, and where we may likely make a mistake. So let me say I have a problem of maximizing x1, x2, x2, x3 plus x1, x3 such that x1 plus x2 plus x3 equal to 0. Okay, now okay, so if I just do my standard operations of computing the Lagrangian and so on, so my L would now be, again, I'm just restricting myself to a single constraint. L is x1, x2, x2, x3 plus x1, x3 minus lambda x1 plus x2 plus x3. Okay, so what we do is we look at the gradient of L with respect to x, and I'll be largely interested in looking at the second or the Hessian of L with respect to x. Of course, with lambda wouldn't matter because it's that. So I'll skip this step. We can try and find what happens when this equals to 0. But what is important here, and this will give me some point x star and lambda star, right? However, what happens to the second derivative or the Hessian? This is 0, 0, 1, 1, 0, 1, 1, 1, 0. Okay, this is of course a symmetric matrix, and I can check. So the second order conditions would see, okay, if I were to maximize, I'm just looking at if this is like less than or equal to 0. How do I do the check based on what I learned from symmetric matrices? I look at the eigenvalues, and the eigenvalues here with computation will turn out that they are 2, -1, and -1. Okay, and this is not very useful for me. Okay, so how do I look at these conditions now, right? So this constitutes what we call as a saddle point. And I think we talked about saddle points last time, if I remember, or not. If not, we can talk about it again. Okay, so how do we check for positive definiteness or negative definiteness and so on? So generally, I would look at D. So if I just take any matrix M in R n cross n, the definition of positive definite so I want to check whether M is positive definite. The definition would say take any x, multiply it with M and x, so this must be greater than or equal to 0 for all x in Rn. Okay, so this is my definition of a positive definite or positive semi-definite matrix. So I don't really directly use that over here because there is a restriction on this D. I don't really arbitrarily go in any direction, right? And the reason why we spend time deriving those directions D and all is essentially because of this also. So I'm only in those regions which are orthogonal to H. Okay, this is my only region of interest. Okay, so this D must be such that it is, so this is must be for all D for which the gradient of H at X star transpose times D equal to 0, right? Which means that this D must be in a space perpendicular to the gradient of H. Okay, this is nice now. So let me see what is H here. H is x1 plus x2 plus x3. The gradient of H is now 1, 1, 1. And now I'm searching for a D such that 1, 1, 1 times D is 0, or in other words, D is in the null space of this matrix 1, 1, 1. Okay. So again, I'm only interested in those D's, not whatever vectors I take in Rn, just like I do in this case of any arbitrary Rn. Okay, so let me now define. So what I know is that this D must belong to the null space of the gradient of H. Okay, now let D. Okay, now if let Z be, say, maybe Z1 till say Zk, such that each of these Z1 till Zk, they span the null space of the gradient H. Okay, for example, if I take this particular, so here I want to find what are these D's. These D's would essentially be the span of -1, 0, 1, -1, 1, and 0. Okay, so the null space of the gradient of H would be in this span of these two vectors. So these two vectors together I will call as Z in general. So 1, 1, 0. Okay, good. Now, how will any vector D in the null space look like? That will look like Z times any arbitrary vector U, right? Or so maybe like U1 times the first vector plus U2 times the second vector, and so on. So I can write this arbitrarily like this now. Okay, now how does D transpose Nabla 2 of L D look like? This will now be U transpose Z transpose Nabla square of H Z U. Okay, now there's a nice structure inside here, right? So this is also This I will call as the projected Hessian, and U is now any arbitrary vector in Rn. Okay, now I check for positive definiteness of the Hessian matrix. Hessian, not just the Hessian, but the projected Hessian matrix. Okay, and that will give me the second order condition. Okay, so to summarize, okay, this was the first order necessary condition, and the second order necessary condition comes from something like this. So this Lxx here would be just the gradient of my Lagrangian with respect to x. Okay, now again these w's, they come from any vector in the tangent space. Okay, slight distinction now between the first and the second order necessary conditions in case of a constraint optimization, even though we are spending time converting the constraint problem into an unconstrained one. Okay. So any questions? Maybe I'm like going too fast or too slow.
Can you please go to that constraint problem is where we are applying that constraint?
So, okay, so I'll just say the summary of whatever I've done, right? So we are starting from here. This is my constraint problem that I'm minimizing a function f of x subject to a set of equality constraints which are mathematically represented as hi of x equal to 0. In the single constraint, I just define my Lagrangian as f of x plus lambda h of x, and then I look at the gradient of L, and then so the first order conditions would just be on this gradient of L. So this is just the gradient condition. And if I have more than one condition, this is how the first order condition like it generalizes to. Okay, do we do we want to do a quick example and check? Yes or no? Yes. Okay. So let me make you do a little bit of this. So we had a penalty method last time, right? Okay. So let's try and solve what these things mean here. Okay. So we had minimize twice x1 square plus x2 square such that x1 plus x2 equal to 1. So what we had done last time was just to motivate what we were doing here. So we had twice x1 square plus x2 square plus lambda 1 minus x1 minus x2. And then what we did was for different values. So this was the penalty we imposed on violating the constraint. Okay, so we started off with when lambda was 0, and then we tried to get the optimal value of lambda was 4/3, and then I could do my regular optimization and find and check values. Okay, now let me try to do this by applying. Okay, maybe we can also take up a pen and paper and do this, right? So what is the first order? So the L here will look like twice x1 square plus x2 square minus lambda x1 plus x2 minus 1. Okay. Okay, so what are the first order conditions that I'm looking at? I'm looking at the gradient of the Lagrangian with respect to x. So that will be, okay, what was that? So gradient of f plus lambda gradient of h at x star was equal to 0. So let me compute the gradient of this. So I have twice x1 minus lambda, and then I'm looking at no, not twice x1. This will be 4 times x1. Then I'm looking at twice x2 also minus lambda, and then x1 plus x2 minus 1. So I'm solving for these ones. Okay, so I don't know. So I have now 3 equations and 3 unknowns. This should give me, okay, so 4x1 is lambda, so x1 is lambda by 4, x2 is lambda by 2. I substitute this. Okay, just check if you do this, if you get back to this optimal lambda, which is 4 by 3. Sorry.
Sir. Yes. 4 by 3.
Do we get those?
Yeah, I got 4 by 3.
4 by 3, right? So I think that is maybe a good.
So that is just the first condition, right?
Okay. Can you compute the second order condition? Second will just be, I think it will be like quite simple here, and because these are all convex, so you'll have 2, 2, 0, 0, 1. This is actually greater than 0. So here we don't need to worry much, because if okay, so I think if I can say this a little loosely, that if second is equal to 0, then this is a sufficient condition. So I can actually conclude something directly from here, as long as this is greater than 0. But if it's not greater than 0, I need to do one more step to look at the to look at the orthogonal space to this constraint. Okay, so what problem we were having here was that the second gradient or the Hessian of H had so where was that? The Hessian of it had eigenvalues which were, how did I miss that? Just wrote it here only. Yeah, here I think here the eigenvalues were like 2, 1, minus 1 or something, right? So this was not so when I have eigenvalues of this point, I just cannot conclude anything, right? But if I get a sign definiteness, I can directly conclude that this will be an optimal point. If it is not sign definite, then I need to do one more step to just check which direction I am moving, and then I have to compute the d and compute the optimal accord. Okay, so there was another example. Okay, let's do whatever we were having here, no? Okay, we'll just do the example and see where we are on this. So the thing was minimize x1 plus x2 such that x1 square plus x2 square minus 2 equal to 0. Okay, so the L here would be x1 plus x2 minus lambda x1 square plus x2 square minus 2 equal to 0. Okay, what do we get from solving the first order conditions? So gradient of L with respect to X is 0 and the gradient of L with respect to lambda is 0. Okay, can someone quickly compute and check how this looks like?
Lambda is equal to plus minus half.
Okay, lambda equal to plus minus half. So which one do we consider? Should we consider lambda equal to plus half or lambda plus minus half? Which one is the one that is useful for us?
Maybe the plus one.
The positive one, right? So
Positive
because we
one.
have to subtract from 2 then.
Okay. Okay, we can I think work this out, right? So this should not be a great amount of difficulty. Okay, so what happens? So I'll just keep around with this example, and we know that the answer is like a -1, comma -1, and so on. So I just keep.
Sir, one question. What is that second gradient condition? Means how in the previous example, how you have calculated that 2101?
Which one? This one?
Just
somewhere I added an extra
In
page.
that above question, only the second derivative, I think. Charu, right? That one only, no?
Yes.
Yeah,
Yes, yes.
it's a Hessian.
On the same page, sir, where we were.
Here.
The current page. Yes,
Okay.
yes. This 2001, right? The upper one.
Okay, so this is, so I have this function only, right? So I think the second derivatives wouldn't show up here because everything here is first order. So I'm mostly looking at only this guy, right? So, so I have this function twice x1 square plus x2 square. The gradient of this function would be the derivative with respect to x1 first. So that is 4 times x1. This is a 0. Then I have 2 times x2. Okay.
Right.
Then the Hessian will just be, okay, this with respect to x1, which is 4. Again, the first function with respect to x2, that will be 0. Second with respect to x1 will be 0. And here it will be a 2. Sorry, not a. Okay. Yeah, 4002, sorry. 4 and 2.
No, sir, I just wanted to understand this process. Okay, thank you.
This is fine, right?
Yes, yes. Okay.
Okay, so I'll still let's still stick to the same problem and see if things will change when I say minimize x1 plus x2 such that now x1 square plus x2 square minus 2, which was earlier equal to 0, has now become less than or equal to 0. So the question that we ask ourselves is, what changes? What is the change that we can directly see? So in the first case, I was looking at so the contours of my function x1 plus x2 is something like this. Okay, And then my constraint set was simply x1 square plus x2 square minus 2 equal to 0, which is, I'm just looking at some set like this. Okay. And my constraint was only on the boundary of the circle. But now I have not just the boundary of the circle, but even the points inside the circle. Okay, so everything inside the circle is also my constraint set now. Okay, first is just by observation, does the minimum change? Just look at just by observation. No any math or something. Just looking at the picture, just by observation, does the minima change when I change this from equality to something now which is inequality? Any answer on this? Just
No,
by
I think
observation, no math and all that.
No,
it
I
should be
think
just a lower tangent. Yeah.
Right? Nothing changes, right?
Yeah.
yeah.
Okay, that's the correct answer. Okay, let me now do something else. Okay, so suppose now I have a function which is, say, like this, and then a constraint set which says, okay, g of x is, say, greater than 0, something like this. Say, or say g of x, some constraint set which is in the following way, right? So all the region to the left of this line is the constraint set. Okay, and then now I'll redraw the same function like this and say now my new constraint set is the same function, but now my constraint set is here. Okay, what is the minima here and what is the minima here? Are they same? Are they different, or doesn't, or can't say anymore?
Different.
They are different. Okay, so what is changing here? In the first case, that my minima is inside the constraint set. So even if I add a constraint, my minima does not change. Okay, here I am adding a constraint, so my minima changes to a point like this. Okay, now this happens when I have an inequality constraint like this, right? In this case, my minima doesn't change, whereas in problem like this, the minima really depends upon where my what my constraint set is. On the constraint set. Okay. So starting from here, we will now derive conditions for minimizing f of x such that now I have inequality constraint g of x is less than or equal to 0. Okay, then I will ask myself a question. Now, what are the necessary first order conditions? Okay, so now first is, okay, I always start with a feasible point. Okay, what is a feasible point? If I go back to here, okay, if I draw some arbitrary points, is this a feasible point for this problem? Point number 1. Is point number 2 a feasible point? Is point number 3 a feasible point? Which of these are feasible points of, say, for example, 1, 2, and 3? Only this and these are feasible points because point number 2 does not satisfy this constraint. Okay, so the only points that are feasible or of interest are the ones which satisfy this constraint set. Similarly, here, the point here is not feasible because it does not satisfy the constraint. Point here is feasible, point here is feasible. Similarly here, this point is of course feasible, this point is also feasible, but this point is not feasible. Okay, so I have to now look at, I start from a feasible point, say I start from this point here, and I keep on searching for a minima, right? Or here I start from here and I keep searching for a minima, or here maybe I start from here, or I start from here and I keep searching for a minima. Okay, now start with a feasible point, and I have to move in certain directions. Okay, which direction should I move? First is my objective function should decrease. Let's say I'm moving along some s direction. Okay. Gradient of f times s must be less than 0. That is what will tell me that I'm actually going along a direction which minimizes f. So this should always be satisfied as long as I am searching for a minimum. Okay, now my constraint set now is g of x, and say I go slightly further away from x, again in the feasible direction. This will be g of x plus gradient of g of x transpose times s. This must be less than or equal to 0, because the search must be along the direction which satisfies the constraint. What is the constraint? G of x is less than 0. In the previous case, this was just a strict equality here. Okay, now that is the distinction that we start. Okay, two things can happen, or three things can happen. First is we ruled out points which are not feasible. This is ruled out, this is ruled out, and this is ruled out. Points which are allowed are the ones where I am here on the boundary of the set, or I am inside the set. Similarly here, I am at the boundary of the set or inside the set. I am inside the set or at the boundary of the set. Okay, two things can happen. Okay, now first is, let's start what happens when x lies strictly in the feasible region. Let's say I am like talking of this example, and say it's lies strictly inside the circle, like really inside the circle. Now, which means if I take a circle and I start strictly inside, not on the boundary, which means any direction that I go, okay, in any direction I go, h g of x less than or equal to 0 is satisfied. Right? Whenever s is small enough, so g of x plus s is f. If x is strictly inside the circle, there will always be a small region. Even though if I'm just here, I can still find a region which is just in the neighborhood of x, such that g of less than or equal to 0 is satisfied. Okay, now fine, this is fine, so that I'm not worried about g being satisfied, because within that region I move any direction, I'm happy. Okay, now what should happen to the second condition? Now the second condition is that my f at the same point should also decrease. Okay, now what does this mean? That okay, this constraint set is kind of no longer, if I can, I'll use this word later also, called active. Then my optimality only reduces now to finding gradient of f at x star equal to 0. Okay, nothing changes. Okay, what does this geometrically mean? This means the following. Let's say if I am inside this region, okay, this I'm talking of this particular case here. the minima is independent of this line now, right? Even if I impose this constraint of gx less than or equal to some number, say 6 or something, minima does not change. Whereas here, minima changes. Here, in the first case also, minima does not change. Which means I'm just happy by looking at the solution to the unconstrained problem, which is essentially this. Okay, now exciting things will happen in case 2 when x lies on the boundary of the constraint. That is, I'm largely looking at g of x equal to 0. Or in this case, x is lying on the boundary of the circle, or x is lying on these points here. Boundary of the constraint set. They are no longer here, but at the boundary of the constraint set. Okay. So when this happens, now I'm looking at g of x equal to 0 and search along gradient of f x times s must be less than 0. And then what must happen with g? G. Now, which directions I can move along g? So if I am on this point, I can move only along directions which are either along on the boundary or within inside. This is not allowed. I just cannot move on arbitrarily any chosen directions. So what changes in the way we now formulate conditions? Okay, so this also means now that gx g of x plus s is now equal to g of x plus gradient of g of x transpose times s. Okay, this is how it is. Now, what should this satisfy? So g of x equal to 0 because I am starting here. What should be the remaining one? This must be less than or equal to 0. So the two conditions that I am satisfying together are gradient of f of x times s is less than 0. Okay, this ensures that I am moving in the right direction, which minimizes f. Okay, and the second condition that I am looking at now is gradient of g x times s is less than or equal to 0. Geometrically, this gives me a open half space, and this gives me a closed half space. Okay, now at some point of time when I keep moving this, I will have to, maybe I'm moving in the right direction along this, I'm moving here, 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 here. Then there's some point of time I have to violate this, right? So now I ask myself a question. When is this violated? Okay, this is the violation happens when the gradient of f times s is greater than or equal to 0. And at the same time, I have this condition, right? Gradient. This always has to be satisfied because this is the constraint and I cannot move outside the constraint set. Okay, now I have two things here, right? I have a vector or an s, which I can also maybe call now. Okay, I'll just do this as some direction, right? A dot product of s with f is greater than or equal to 0. Dot product of f with the gradient of g is less than or equal to 0. Okay, what can these two together mean? Right? Which means that for a given okay, so when is this established? This is established only if gradient of f and the gradient of g are in opposite directions. Earlier collinearity was enough. if they are in the both in the same line, not without worrying about the directions, we are fine. Okay, so which means we are looking at both moving in the opposite directions. Okay, which means now gradient of f and the gradient of g will have opposite signs. Mathematically, I can write this as gradient of f, gradient of g is equal to 0, with mu being strictly greater than 0, because this should be in opposite directions, and therefore gradient of f and gradient of g have opposite signs. Okay, at the optimal. Okay, now this is 1, this is 2, and then I have the third condition, g of x is less than or equal to 0. Okay, we can slowly try to understand the subtleties of what is different in what we did earlier and what we are doing now. Okay, so how do I now write down my my general conditions? So I am now looking at this condition. This is my so I'll just write down again gradient of f plus mu. Okay, so should be gradient, right? Gradient of g of x should be equal to 0. This is my stationary condition. Okay, and then mu must be greater than or equal to 0. This is called the dual feasibility. Third, I know is that g of x is less than 0. This is my given constraint. I will call this as the primal feasible condition. Okay. Now, two things can happen, right? For example, so both these conditions should be satisfied, right? That when my minimum is inside the constraint set or minimum is outside the constraint set. In this case, here, I do not need to compute the gradient of g. Doesn't really matter because I am only dealing with a function with constraints which are where the minima is within the constraint set. As opposed to here, the minima actually changes, which means that either mu, so when in this case, if I just set mu equal to 0, then what happens? Well, it just turns out to be an unconstrained problem, right? If I just set mu equal to 0. So two things can happen. Either mu is 0 or g of x is active, which means I am on the boundary. Here, I don't really need to compute, I don't really need to compute the gradient of g because just computing the gradient of f is sufficient. Here, which means, okay, I can just simply plug in mu equal to 0 in the conditions and get my condition. If this is not case, then I am at the boundary of this thing. At the boundary here means I am looking at g of x equal to 0. Okay, so either mu equal to 0 or g of x equal to 0. Together, so this or this. Together, mathematically, I can write this as mu times g of x equal to 0, which I call as the complementary slackness. Okay, now this,
Gradient, right? Gradient.
sorry?
Here you have mentioned mu into g of x, so it will be mu into gradient of g of
No,
x.
I'm not worried about gradient of x. So two things can happen, right? When I'm at the boundary of the feasible set, gx equal to 0. This is a constraint that is being satisfied, like here, right? Here on this line, gx equal to 0. It's not less than, right? So,
Okay.
which means mu is not equal to 0. Here I need to compute the gradient. And that gradient shows up here in the first line. And in the other case, when mu equal to 0, I don't need to compute the gradient because I'm well inside the feasible region. My minima is also inside the feasible region.
Okay.
Okay, now I can slowly generalize these two multiple inequality constraints. Say now I have minimize. So I'll write a very generic condition now, minimize f of x subject to g1 x till say some g mx less than or equal to 0, h1x to some say h p of x is also less than or equal to 0. Okay, now I can write my general condition. So L will now be f plus summation over lambda hi, the equality constraints, summation over mu I gi, the inequality constraints. And what are the first order conditions now? I'll just sum of both of them. Gradient of f plus summation lambda I, gradient of hi plus summation mu I, gradient of gi is 0. Only constraints are on mu I to be greater than or equal to 0. Gi constitute my inequality constraints. Hix equal to 0 constitute my equality constraints, and together with whether to check the constraint is active or not, I will have this complementarity slackness conditions. Okay, now this is my general criterion to check for necessary conditions for existence of minima of a system or a problem which has both equality and inequality constraints, and these are also broadly referred to as the KKT conditions.
And
Okay.
above h also equal to 0 or less
Sorry?
than equal. H,
Sorry?
h1x,
So-
hpx less than
Okay,
equal
sorry.
to 0.
Sorry. This is a mistake. Sorry. Thanks for that. So H is only equality constraints equal to 0. Sorry about that. Okay, so just to summarize what is on the slides now, so we start off here. We have some minimizing of f of x, equality constraints, inequality constraints, all the set of stories that go now to just write down these as my general conditions for optima.
Sir, these conditions will be for global minimum.
Local.
No.
Here.
So there will be conditions on like lambda I also, right?
No, lambda can be whatever. Because we are not really worried about the lambda was so mu. When I was looking at mu, the only condition was that that the gradient of f and the gradient of g need to have opposite signs, and therefore I strictly put the mu to be greater than 0. Whereas in general, we never imposed any conditions on lambda.
Here it is mentioned, right? Lambda I is
Okay.
greater than 0.
May not be strictly required.
Okay.
Okay, and then the second order conditions will still be like the same. So okay, let me try to do. Okay, I'll see if this problem is easier to solve, or we'll just do a couple of problems to see how to solve this now. So most of the times we are happy formulating problems, but let me see. Okay, this is fine. I think we can just look at this problem. So I have a cost function to be minimized, which is quadratic, and such that these two conditions are satisfied. So I can write these conditions as inequality conditions like let's say x1 plus x2 I can write this as x1 plus x2 minus 3 greater than or equal to 0, or also minus x1 minus x2 plus 3 is less than or equal to 0. Similarly with the last one. Okay, now let's slowly understand what each of this means. Of course, this only has inequality constraints, not equality constraints, and this is a little more challenging than this having inequality constraints, because we need to find out if the minima is inside the constraint set or on the boundary of the constraint set. Definitely it will not be outside. Okay, so this is my f, my mu's, and these are my functions. Okay, and this minus signs take care of making the these to be written as constraints which are less than or equal to 0. Okay, so we'll slowly solve this. So first I'm looking at, sorry. Okay, so I'm looking at now the gradient of this with respect to x1. So that will be twice x1. Here will be minus mu1, and here will be twice x1. So I'll have a plus mu2 x1 equal to 0. Similarly, this will be the gradient of L with respect to x2, and this will be my two constraints, and these are the complementarity conditions with mu1 and mu2 greater than or equal to 0. Okay, now just by writing these conditions will not tell me if my minima is inside the constraint sets or on the boundary of the constraint sets. So let us see what happens. So case 1, what I check is that there is no active constraint, which means both cases G1 is less than 0 and G2 is less than 0. What happens in those cases? I am now just interested in without this. I'll solve without constraints, because these constraints are redundant, because I assume that the minima is inside the constraint set. Okay, which means, so at the moment I do not know, right? What I do not know is the minima within the constraint or at boundary. It could also happen that it is within the minima of something, but at the boundary of some other set. Both can happen, right? It's not that both mu's are non-zero or both mu's are 0. It can be that mu1 equal to 0, which means G1 is now redundant, and mu2 is not 0, because, and then in that case G2 might be equal to 0. Okay, so we'll check each of those, right? What happens? So first, I'm assuming that both constraints are strictly satisfied, that the minima is in the inside of those constraints. So I'm just looking at a general unconstrained optimization problem, which means x1 star and x2 star are equal to 0. Okay, when x1 star, what happens in this case? Is this a useful solution? If x1 star, if both are equal to 0, does it just check if this is satisfied and this is satisfied? So these two must be satisfied, right? So when x1 is 0, x2 equal to 0 is point number 3 satisfied. If x1 equal to 0, x2 equal to 0 is point number 4 satisfied. The answer is no, right? Because I will not have that 0 is not greater than 3, or 1 minus 1, 0 is not greater than 1. So this is not very useful to me. Okay. So I'm assuming that there will be no solutions where both mu1 and mu2 equal to 0, or that the optima is within both strictly inside both the constraint sets. So I'm just now searching, right, for in a ad hoc way. Okay, case 2, what I assume that the first constraint is active and the second constraint is inactive, which means that if I'm looking at two constraint sets, let's say the first constraint is, say, something like this, and the second constraint is something like this. Okay, then I'm assuming that the minima is well within this set and at the boundary of the second set. Okay, so that G1 is, sorry, G2 is strictly less than 0, and then G1 equal to 0, which means mu1, sorry, I think it's the opposite. If mu2 equal to 0, then okay, so okay, sorry. So we had mu1, G1 is 0, mu2, G2 is 0. So when mu2 is 0, then G1 is okay. G2 is strictly less than 0, and because mu1 is not equal to 0, G1 must be equal to 0. Right? Mu1 is greater than 0, which means the only possibility for this to satisfy is G1 equal to 0. So I'm asking myself, is the optima on the boundary of G1 and the interior of G2? Okay, that's possible, right? Okay, then I just say mu1 is greater than 0, mu2 equal to 0. I solve and I just get this solution that in this case x1 star x2 square is 2 comma 1 and mu1, which is equal to 4, is greater than 0. I just put it back and check if these are nice. Similarly, I look at the second constraint is active, but the first constraint is inactive, and I get minima solutions as x1 star x2 star is 0 1, mu2 is less than 1. This is not allowed because I always want my mu to be greater than 0. So this is a bad thing that has happened. Then I say, okay, both constraints are active, in which case I have a solution of the form -2 and 5, and I get a couple of those solutions, and I keep on doing this. So I get okay, something bad happens here also, right? That mu okay, yeah, sorry, this is kind of okay, I think. Okay, so for each of those possibilities, I check whether my feasible set is whether my each of these conditions from 1 to 6, 1 to 7 are being satisfied or not. Okay, so case 1, x1 equal to 0, x2 equal to 0. We saw it violates both the constraints, so not very useful for us. Case 2, mu1 greater than 0, mu2 equal to 0. First constraint is active. Okay, this kind of violates 4. You can just check with these 2 points. Case 3, mu1 is 0, mu2 greater than equal to 0. I get something this, which is violates 3 and 7. Case 4, where both constraints are active, then x1 star x2 star is -2 and 5, and this one, right? Now we'll check for each of those points. For the first point, I have mu1 plus 4, mu2 is this goes here. The only condition that is now satisfied is x1 star x2 star is 1 comma 2, which means mu1 equal to 6, mu2 equal to 2. So two things are happening here, right? Mu1 6, so condition number 7 is satisfied. For x1 star x2 star, this is also satisfied because x1 plus x2 equal to 3, which means x1 plus x2 is 3. You look at this carefully, right? I am now replacing this greater than with a strict equal to here. And then for the same point 1 comma 2, x2 minus x1 square is also now equal to 1. Okay, so both these are now replaced with strict equality, and that the minima occurs at the boundary of both G1 and G2. Okay, just read through this and let me know if things are clear or not. And I think these slides are with you also. So I think I at least posted to Achal, and I'm assuming she would have shared with everybody. Okay, any questions of just look at all these cases which are happening. Okay, if we have a few more minutes, can we try and solve one more similar question?
Yes, sir.
Okay, I'll make you solve. Okay, so quickly, so I have to minimize f of x is, so look a little long and ugly, but nothing to be terrified about. 3x1 square plus x2 square plus twice x1 x2 plus x1 plus 6x2 plus 2. Okay, nothing to be scared. It's a pretty friendly function itself. So such that twice x1 plus 3x2 is greater than or equal to 4. x1, x2 is greater than or equal to 0. I can rewrite this as inequality constraints like g1 is minus twice x1 minus 3 is x2 plus 4 is less than or equal to 0. G2 is such that minus x1 is less than or equal to 0. G3 is such that minus x2 is less than or equal to 0. Okay. Now I know how to write the Lagrangian for this. I need to compute the gradient with f. That will be, let's look at this one, 6 x1 plus twice x2 plus 1. And the gradient with respect to x2 will be twice x2 plus 2 x2 plus 6. Gradient of g1 is, again, look at this carefully. So we have minus 2, minus 3. Gradient of g3 is minus 1 and 0. Gradient of g4 is 0 and minus 1. Okay, nice. So first I assume that all constraints are satisfied, which means that the minima lies in the interior of all those constraint sets, G1, G2, G3. For example, if I were to quickly draw those constraint sets, I will have, so x1 is greater than 0, which means I'm looking at this region. X2 is greater than 0 is at this region. 2x1 plus 3x2 is greater than or equal to 4. Okay, how will this look like when x2 is 0, x1 is 2, and when x2 is 0, x1 equal to 0, when x1 equal to 0, x2 is 1 by something like that. Okay, so this is that line, and then I am looking at my constraints being somewhere here. Right? This will be the region such that 2x1 plus 3x2 is greater than or equal to 4. Okay, just check if I am doing it correctly or if it is inside. Okay, so if I assume that, okay, if I assume that, I'm assuming that I'm just drawing it right, that all the constraints are strictly satisfied because nothing is on the boundary. What are the boundaries of this set? This is the boundary, this is the boundary, this is the boundary, this is the boundary, and so on. Nothing happens on the boundary, that everything happens in the inside, which means I need not really, so all my mu1, mu2, mu3 are equal to 0, which means I just look at the minima of the function by itself without any constraints. So this gives me a solution that if I just plug in quickly gradient of f equal to 0, this gives me 6x1, okay, x1 is 5 by 4, x2 is minus 17 by 4. Okay. Is this a good solution? Where x1 is 5 by 4, x2 is the negative of 17 by 4. If yes, how? If no, why not?
Not in positive quadrant.
Not in positive quadrant, because what condition is violated is x2 is not greater than 0. Okay, then I can look at make G1 and G3 as active constraints. Okay, which means I'm assuming that it is, what is my G1, that it is on the boundary or somewhere here. This is the point where what is G1 equal to 0 would be minus twice x1 minus 3x2 plus 4 equal to 0. And then G3 is active. G3 is active, which means x2 is equal to 0. Okay, which means I'm at the boundary of these two regions. So this is the constraint of x1 being greater than, so this is this line is my G1. X2 being equal to 0, x2 being 0, this is G3, is it correct? And then this is G1 and so on. Okay, so if I have these two constraints that are active, then what happens? Then I'm looking at, I not only solve for the gradient of f, but now I'm also looking at, because mu1 is no longer equal to 0 and mu3 is no longer equal to 0, I am looking at solutions to this. Okay, such that this holds together with G1 is 0, G3 is 0. Okay, so I'll let you do the steps for later, but I'll just write on the solution that I have. So I have x1 is 2, x2 is 0, mu1 is 6.5, mu3 is negative of 9.5. Is this a good solution? Okay, you will check each of them. Is the constraint on x1 satisfied? Well, x1 is greater than 0. Constraint on x2 satisfied? This is also okay. Is the constraint on mu1 satisfied? This is true. Is the constraint on mu3 satisfied? Well, no, I have a negative here, right? All my constraints were that mu i's must be greater than 0. Okay, now we will look at one more condition and kind of slowly exhaust all of these options. Okay, now what I also would now look at is drop this constraint G3. Okay, and then check when only I have, so this is also gone. Repeat the same exercise for gradient of f plus mu1 gradient of G1 equal to 0, and then repeat the process. And we can discuss on this solution when we meet next time. Okay, just on time, so I'll just stop here and take questions. So what I would like you to look at, if at least to understand the entire process, is try to work out at least this example by yourself. And then we can start discussing. Unless you do it by hand, you will not get the feel of what all these cases are and so on.
Yes, sir. Yes, sir. Exactly.
Please do that.
We'll
And
try
then
to
next
do
time, so what I'll do is maybe before we meet on Monday, I'll just post some small problems so that you can attempt those and we can solve from where you're having difficulties. Otherwise, this gets a little too one-sided for me to just keep speaking and not really understanding whether you're following it or not. So I'll maybe just post a couple of 3 or 4 small problems. just to submit our understanding into these things, the first order necessary conditions, second order sufficient conditions, and so on.
Sure.
But till then, just have a look at these slides and just at least write this example is there, and then there is one thing also here. Just try if you can solve this by yourself.
Okay.
Okay, good. Thanks.
Thank you, sir.
Thanks, sir.
Yep, thank you.